first slide, I have here sort of what that's for the chemical educators. What is it actually that Odyssey as a support tool for chemical education is trying to address. So I don't know if you're familiar with this whole terminology of Johnston, which is, I mean, he is, if you go to schools of education, he is considered like a god there, who came up with this, this analysis of chemical education that you're dealing with the 3 dimensions. And the biggest problem for students is making the connection between the 3 dimensions. And so for the molecular level, Odyssey allows you now, to see something that's the molecular level otherwise is invisible, and so it's to emphasize, it's a support tool. So Odyssey is not like it's not a curriculum, that's going to replace a traditional textbook or anything like that. It's a support tool to add to the arsenal, of tools you use in education. So this slide shows really what sets the program apart from, there's so much electronic stuff now around. So it's interactive 3D simulation, visualization simulation. What we do is always at the molecular level. I mean, there are a lot of tools where simulate lab benches and all that stuff. We don't do this. I mean, it's strictly a molecular level program, molecular modeling program. Our stuff is calculation based, so we don't have videos produced by basically artists' conceptions of chemical phenomena. Everything we do, there's always a scientific calculation behind it, and so that makes it really resemble, or it literally is very close to real, in quotes, molecular modeling programs. So it's not a toy. It's a real the teaching equivalent of a real molecular modeling program, and our models are always explorable. That is a huge difference to all the videos, are used widely these days. And obviously with video, all you can do is watch it again, rewind it and watch it slow and watch it fast. But our models you can actually interact with. So this slide here is an important one: computational chemistry in disguise. That's what the program does. So there are two computational engines in the program. One is quantum chemistry. That is actually, it's sort of borrowed from Spartan. It's like a mini Spartan that's inside the program, or mini Gaussian if you wish. And then there's a classical molecular dynamics simulation engine. So these are two back-end modules, but there's an easy to use interface sits around it that there are no setup panels or anything. It's zero jargon. It just you just hit a button and it's there. And then around that sits a lot of content, chemistry content, that I can show in a few minutes. So now, if you are Dr. Kishore, yeah. I think you are a computational chemist, and you are. Yeah. You might to make clear, it's, even though you will immediately relate to a lot of stuff that's in the program. It's not a computer. Yeah. It uses computational chemistry. It doesn't teach computational chemistry.
Okay. Fine.
That is by design. So.
Okay.
So last slide, what can you do with the program? You can build models from scratch and query them. So we'll start with that in a minute. And we can go into the archive of the program. There are about 3,000 models are, that ship simply with the program when you install it. They're sort of canned demos, which are included with the program. They're sort of scripted things where you go through a sequence of steps in order to show a specific phenomenon. Or you can assign student worksheets now for a computer lab. Now that obviously requires that the students have access to the software, so that you have it not just on the on the instructor computer for demonstration purposes. So if the students have access, then they can work through these guided labs. That's what they are. The types of models in the program, there are 3 types. Small molecules, that's sort of the world of Spartan and Gaussian. Bulk phase models, so that's something you wouldn't typically have in a traditional quantum chemistry program, because you can do quantum chemistry easily for large models, solids, liquids, gaseous solutions, up to 1,000 atoms, so you can handle pretty routinely. And then we have tools also for a few examples of simple biopolymers, polypeptides and polynucleotides. Okay, that's my, I'll end the PowerPoint slides and jump into the program. So if you install it very first time, this is going to be the initial screen. You see at the top of there's a tool, there's a button bar there. New users, demos and visuals, guided labs, concept applications, molecular stockroom. So that's the highest level navigation tool in the program. It's by default, it's set here to, featured demos and visuals. And we'll, here you see specific questions which I addressed. This was in my PowerPoint slide, demos are specific phenomena. These are demos, that answer the question that you see here, how are hydrated cations different from hydrated anions, or why are AX3 type molecules triangular, and so on. I'll guided labs, these were the student worksheets, and the new users, I'll show in I'll go to new users, and then we build a model. Okay. Typically after you install the program, or imagine a student installs it on his or her computer, and they're supposed to learn about it. The logical thing is, or anyone who you go to new users, you hit on topic 1, viewing samples in 3D, and no, these days with students, it's so largely so intuitive that you don't need to read through the text on the right side. Left mouse button rotates, right mouse button translate, zoom, middle scroll wheel the scroll wheel zooms. If you have a touch screen, the pinch gesture zooms too. These are things are explicitly documented here also on the right side of the screen. I can go to the next tutorial, running simulations. So here's classical molecular dynamics simulation, stop go button below the model. Simulation time, lower right corner, 0.67 times 10 to the minus 12 seconds, picoseconds. Okay, so picoseconds up to nanoseconds. That's the time regime you are in that you have in the program. So chemistry that happens up to a nanosecond time scale is accessible. You can't do computer chemistry here, which takes a minute or something like that. It would take an astronomically long simulations. And the next one here showing the electron cloud. That here is, so the last topic was running classical simulations. This here is carboxylic acid, and here instructions. I go to to an icon in the icon bar. I select first low density. This is now the what's running there is calculate the wave function, square of the wave function. Here's the electron distribution. We use the word electron cloud in order to avoid all the terminology of quantum chemistry, because it's a program that's used widely, and quantum mechanics is a very intimidating thing for many people, and so we try to use earthy language. So it's electron cloud, and then polarity map. This here is in the world of Spartan and also Gaussian, electrostatic potential map. Electrostatic potential map is sort of a mouthful, it's even though it's no, in organic chemistry books you see the language being used, but electrostatic potential map, very high, very intimidating. So this is here is replaced by the word polarity map, because that's basically what you are after. So red color negative, blue color positive, and so on. Okay, so here they are. If I go to home, here they have a whole bunch of tutorials, that explain how to work with the program. Now let me jump quickly here into building. So that's my list of what can you do with a program. That was my first item: build models from scratch. So this is what I can. Now we will do first something Spartan or Gaussian-like, namely build a simple organic molecule. So here, if I build, let's say here, isopropanol, okay. So here, I close the build panel. You saw here, why Spartan is so famous, so easy to use. I didn't count the number of I mean, the build is shared with Spartan. I didn't count the number of mouse clicks. There were maybe 4 or so. It's a really easy, even for a child, to build something like that. So here, isopropanol, I can here now do the room temperature simulation. The temperature can be changed by default. Everything is room temperature, or for gases, 1 atmosphere pressure, and so on. And when the simulation is stopped, I can calculate from scratch, again, the polarity map, electrostatic potential map that you see here, which is, the thing that organic chemists care about so much. When I restart the simulation, the electron cloud, the wave function goes away, because now we are in the classical world. Solving the time-dependent Schrödinger equation is still a little bit off. They will come, once quantum computers have arrived. But so now it's classical, basically integrating Newton's equation of motion, classical simulation. And the moment here I hit this, an instantaneous, a snapshot, of quantum chemistry. You as a computational chemist, so what is the level of theory here? It's a Hartree-Fock calculation. There's no correlation at 321G. So it's something you saw. It was we cap it at 30 atoms. So if I make this, I go back to, I modify my model here. Shows you a little bit, how to work with the program. I go to add atoms. No, I want to, if I add here, make it a longer alcohol.
So here you can't change the level of the theory, no?
You cannot change the level of theory. It's all behind the curtain. It's all, we wired it all up. They are all, so it's not a it's not a program, as I said earlier, to teach computational chemistry. It's making it, usable for people who have no clue, what's, if you want to do that, that's our other program, Spartan, opens up that world. No, actually. So here I've built, you see in the icon bar here now, this here is faded out. If I'm circling it, I hope you can you actually see my cursor always move around?
Yeah.
Okay. I'm circling. No, it's faded out because we have gone beyond 30 atoms. So we cap it at 30 atoms. So 2 restrictions. A, it's all, you can choose the level of theory, and B, up to 30 atoms only. But it's all instant satisfaction. It always finishes within less than 60 seconds. Something. I mean, you'll if I chop off here. Oh no, I'm already below 30. So here if I count number of atoms, add property here, just a little glimpse here, total number of atoms. So there. Oh yeah, I'm here right at the limit by 30 now. So here I'm starting progress bar at the bottom. 1001, 1002, 1003, 1004, 1005, 1006. So maybe 10 seconds. There it is. So that's so even on a slow old laptop, it will never take more than a minute. For so so yet now I will here this was so building small molecules, the world of organic chemistry, also inorganic. If I go here back to the build panel. This here was the entry-level panel from which is shared with Spartan. Sort of that's organic oriented. There's an advanced panel which gives you access to all the elements of the periodic table, for doing complexes and stuff like that. There's an option here for ligands and so on. There's the possibility to build solids. I'll show in a minute. Right now I'll go back to entry level. Chop off here, go back to maybe make it ethanol. And now if I double click on the background away from the model, I start a new molecule on the screen, but they're still in the same space. I mean, they interact with each other. I minimize the energy. When I start now the simulation, this year, is now big for teaching. These two things. Intermolecular force is active because even it's classical model, but we don't need quantum chemistry to describe, the hydrogen bonding between these two successfully. So you see here they stay. If I pull this apart, if I stop the simulation, I can use my I can use the mouse holding down the control key. I can move either the left fragment or I can move the right, either the right fragment or the left fragment. Other style.
If you change the orientation of water molecule, how long it take? If you change that.
Say that again.
If you put oxygen away from this, just behind that hydrogen, just change the orientation of the water molecule. Just want to see that how much time it takes. Water molecule. If you change.
Okay.
Just rotate the water molecule so that the oxygen goes away from.
Okay.
If the hydrogen is
I mean, it's the hydrogen bond. The visualization goes away after it's a hard coded number. We check for orientation and distance, and the force field does not. I mean, the force field uses the force field. If I do charge labels partial atomic, you see them. There are partial charges sitting on the atoms. I mean, that is always active, and I mean that's the miracle that complex substances as complex as water can be successfully modeled. With a simple partial charge model combined, with a sort of a Lennard-Jones style, even though it's a more complex, but Lennard-Jones style potential function for steric interactions. So. I can here. I'll turn off here to charge label. Show you quickly other. I can highlight dipole arrows in the model. I can show lone pair positions. This here is sort of something I always sort of cringe a little bit showing that, because if I mean, this is a total cartoon. But so many instructors want it that way, so we visualize literally the lone pair by showing the two little spheres. I mean that requires really pushback on part of the instructor to make clear that this is a cartoon. This is not what lone pairs really are. It's just this is a cartoonish representation that denotes the lone pair positions. So I'll turn this back off. And turn this back off. And I can also now go to, so this is here, ethanol water mixture. I can now go from here to a bulk phase model. So let's say, a mixture of ethanol and water in a flask. So now our flask is going to be a simulation cell. I'm going to put there 50 molecules of water and maybe 20 molecules of ethanol. How do I do this? I go to edit. I go to build a simulation cell. By default, models are in vacuum, so I switch to liquid, and temperature 25 will be fine. The density is an input parameter. I'll pick a density of 0.95, something like that. Then here I have to declare how many molecules do I want of each. So I put 20 ethanol molecules. I put 50 water molecules. And I click on apply. And you see the progress bar at the bottom. And here's my model. You see the scale here, nanometer, always shown in blue for simulation phase models. So this is here, if I put it on space filling, you see actually, oh, this is a bonafide. This really is a liquid phase model. I can go back to tube if I put it here on hydrogen bonds. So here's now why it's ethanol and water, miscible in all proportions, because hydrogen bonding, it's ethanol fits in perfectly, can easily fit into the hydrogen bond network of water. If I start the simulation, you see, the dynamics of fluctuate, bonds break and reform at all times. I can highlight if I want to show the two select group. If I select here the ethanol component, And change the style of that one to, let's say, to ball and spoke. So, okay, that didn't. I now changed it to because the I think because the it's sort of delayed now because it's running with feeding it all into Ring Central meetings. If I select group, select the ethanol again, and change it to tube. So now it's the waters are shown in space filling, the ethanols are showing in ball and spoke. So I mean, you can customize the models in many different ways. Very useful is if I select a molecule, here water molecule, and I can put right click, I can put a clipping center on top of that. Now I'm just showing one molecule. You see how I can focus in on, so here I'm now showing a clipping sphere around my selected molecule or selected atom in the system. So everything is still there, but I can, if I run the, if I only show this much, I'm now showing, I'm just showing here, I'm focusing, you know, on the dynamics, you know, in a small selected part of the system, even though everything else is still there. If I turn off the clipping, you know, here's the simulation of the complete system. And here's just my, so there are all kinds of sort of gadgets, you know, that allow you to visualize, to highlight various phenomena. Okay, let's, I'll go back to the build panel. Well, I'll start another new instance of the builder and show you the one solid model and one biopolymer model. So okay. For solids, here I go to solid build panel. Now solids, this is a build panel in quotes. Proper building of solids, you would have to, you know, we would start out with a space group, you would start out with concepts which are not part of first year chemistry. So what we do is use templates simply. For example, here, if I go to the, you know, the sodium chloride types selected by default. If I just click on the background, it builds the NaCl lattice, but I can now change this, you know, from sodium to potassium, and from chlorine, you know, to bromine. Double click on the background, and then I can choose how many replicas of I want in the given direction. So it's sort of a builder, you know, for the main structure types that you might care about in first year chemistry, and then, you know, change the elements. But you cannot, you know, do arbitrary structures because it simply it introduces lots and lots of complex. I mean, it's the concept of space group is unavoidable, and I mean many people run away from space groups, you know, I mean, at all costs. So, finally, the biopolymer models. If I go here, if I go to nucleotide, so a short strand of nucleic acid. So if I select here, I can select clear an arbitrary sequence. Up to 30 base pairs is fine. Total number of models, you know, the rule of thumb I always tell people, you know, up to 1,000 atoms. If you go beyond 1,000, the program will accommodate up to 10,000. But things get so slow, you know, it's not recommended. But here, so I've built this from scratch for this particular sequence. And I can here two hydrogen bonds, or I can highlight the ribbons here in the DNA double helix. And if I hold down the control key, you know, I'm doing conceptually the same that I did earlier, you know, with the ethanol water pair. I'm moving one fragment relative to the other. I can highlight, I can illustrate here, you know, in an interactive fashion that, you know, the two strands of DNA are not covalently bonded. DNA can unfold, you know, totally essential for, you know, its biological function. You know, otherwise the transcription couldn't happen and replication couldn't happen either. So if I start the simulation, the simulation, this clearly the having it feed into the, yeah, oh no, it's starting up. There's always slight delays here because the also the recording is running. This is now a simulation in the gas phase. So that's of limited scientific significance. It simply falls apart because you are not a biological medium. There isn't water there. There are no chaperone proteins there, and all that stuff isn't there. It just falls apart. Even though biologists, call it DNA melting. So there's a little bit to do with it. Okay, that was the build function of the program. I had on the fourth slide, the second thing you can do with the program is you can retrieve pre-built models. One way to get them is to go to the molecular stockroom. I went here. This is like a tab browser. This was the third model we worked with. Second model, first model I built. This was the tutorial pages I had gone to, and I'm back here at the it's a home. On the home page. What's running is basically a web browser, but it's not because we use it as a navigation tool, but it's not a web-based program. That's something that's often misunderstood. I mean, this is a locally installed application, which does not use the internet. So it's locally installed. We just use the tools of the browser world because that's what everyone is familiar with. So I now go to molecular stockroom. Here's, you have access of about 1,000 compounds ordered according to element models. Here, if I go in the most interesting one, always carbon. So the in the stock room. So for graphite, the model of the graphite, you can see I'm moving the layers relative to each other. Hexagonal symmetry highlighted. Unit cell of graphite, the packing within the layers, the primitive cell of graphite, which is always people have trouble, distinguishing between standard unit cells and primitive unit cells. Same for diamond, unit cells group of 8, unit cell packing within the unit cell. Buckminster fullerene. Here's actually a model of the substance, as you have it as a powder, not just of the single bulky molecule that always everyone shows, but the complete thing. This year is getting awfully slow now because I'm violating my 1,000 atom rule. This is more than 1,000 atoms. So here, of course, then also the if models get very big, things get, slow. It also depends on how good your graphics card is. So it wasn't a good idea now while being plugged into the same when you plug into a projector in a lecture hall. It's rather, you have to be more conservative how big the model should be than if you run it on a laptop. So here's the model of fullerenes, nanotubes, graphene. So this was all in the stockroom, models of carbon elements. Here, inorganic section, let's see quickly sodium compounds as an arbitrary example. So various, these come largely from the from various inorganic databases, which are available also on the web. So here it's just the models are sodium hydroxide, sodium nitrate, sodium oxide, sodium sulfide, borax, and so over 1,000 compounds of stuff. Home, go back here. There's an organic section, a mixture section. You can believe me, that's so the organic section you will have here carboxylic acids, aliphatic, formic, acetic, propanoic, butyric, caproic, and so on. And then in the mixture section here that actually gives me a chance to show something quickly. If I go to aqueous immiscible. Okay, here's carbon. Let's do carbon tet and water. So showing here the interface between carbon tet, and so here now the one thing that requires a little 1 minute explanation is if I do this. So I turn the test tube around. Now my carbon tet is floating on top of the water. What's wrong? Well, what's okay? What's the deep reason is simply it's not because we don't know how to include gravity in the program. It's easy to do. The point is that gravity, I mean, this all that you get neat interfaces between two immiscible liquids. It only happens in the field of gravity of Earth. It doesn't play any role on a time scale of picoseconds. You have to be on macroscopic time scales for this to happen. You can sort of justify that to students if you think about Millikan's oil drop experiment, 100 years ago. They were watching the oil drops, as they were falling, they were looking at them. So it doesn't, on a time scale of picoseconds, nothing happens. So, so the system behaves as if you were, in outer space on the International Space Station, and if you do an experiment with carbon tet and water, they will still separate out, and even in a test tube on the space station. But you can turn the test tube around, and the densest component won't sink to the bottom. So this is also explained in the program in some places. So that was the stockroom retrieve pre-built models. Okay, then third line on my fourth slide was use pre-built demos and visuals. So these there's a featured list. Here there are 21 items, sort of the ones which are presumably of greatest interest. I mean, this is an arbitrary selection in a sense. Complete list brings me here to a list of 56 topics. This is constantly increasing. There's a new release every few months where there's more. And I can also create a custom list. If I go to custom list, edit, I can pick one. How can ionic compounds be represented? What is the limit of saturation for salt and water? And what is the energy of a vibrating diatomic molecule? Arbitrary, select edit. So now I have a list here where my favorite topics. That's sort of useful for instructors if you use it in a classroom. How can I find things? You can, the ones you want to use, you can put in your custom list. So if we now arbitrarily look at these here, how can ionic compounds be represented? So here's this is deliberately very, very terse and very. The idea is to just pull up a model and make a point. Okay, not. I mean, a lengthy maybe explanation of a single phenomenon. It's not a can of worms, but a specific scientific point. So here's space filling models of sodium chloride. Here's actually classical. On the left side, classical spheres. On the right side is the true answer, calculated with Spartan. The square of the wave function, the electron cloud, as they surround the anions, cations. Here's the same ball and spoke and ball and wire, two representations. And here's the explanation that the electron cloud model was include 96.7% of the electron density, 3.3% were outside here, were in between the space between these, because I mean, things are never so completely black and white in the real world, unlike next one here was I had picked completely arbitrary. What is the limit of saturation for salt and water? Here are two models on the left side of a standard solution of sodium chloride, 1 molar, and on the right side of 6 molar is about what you can fit in. And here you get, this is to convey a feel, an intuitive feel, what it actually means if you have, a 1 molar solution, which we deal with all the time. And this is if you work really hard to dissolve as much as possible in it. You see, I mean, there are an awful lot of ions there, and it actually makes sort of a hand-waving argument why, you cannot, activity coefficients and stuff like that, do play a role. It's not, we are ion-ion interactions and solutions are not negligible. So I mean, beyond. And here, number 3, what was the energy of a vibrating dom? This here is simply so it's a little bit sort of almost physics class. So here, the computer measures the potential and kinetic energy. You have a classical vibrating sphere. I can also make a plot, XY plot. If I put the time on the x-axis, and let's say I put the potential energy on the y-axis, and you can see here on the left side, I could do the same plot here for XY plot for let me add one time kinetic energy molar. So now I will. So if I stop this now, it's wherever there's a peak here, there's a valley here, peak here, valley there. Therefore, they add up. Energy is conserved. The total energy, which is simply here the sum of the two, is constant. So we are in the the first law of thermodynamics. So these are three arbitrary examples. If I go back here to complete list of what we call demos and visuals the topics from the first year chemistry curriculum. There are topics where modeling can actually help you understand things. Even though this is the sequence of chapters in a standard introductory textbook, chemical matter, sort of the first 20 pages, atoms, periodicity, chemical bonding, gases, liquids and solids, solutions, thermochemistry, kinetics, and ending always with the biological section. That is the sequence you see in a standard textbook, but we are not trying to cover every topic in the book. For example, you will not see there's no nuclear chemistry chapter here. There's no electrochemistry chapter. There's very little on stoichiometry, for example, because these are things where modeling is sort of a very limited value. So we cover the topics where modeling will, working with molecular models will help the teacher, actually get something across better than, without using modeling. So, but we are not trying to do, there are so many, textbook websites now where they try to have a little thing, for every topic in the book. They have 1,000 little things for every topic. We are not trying to do this. So we only cover the ones where there's something, there's actually something to be gained. Sometimes more and sometimes less, but where's something. Nevertheless, it still sort of parallels, what you sort of the flow of the in the textbook. Guided labs, last one. Then I'll finish my little walk through the program. Guided labs. These are, if I go to complete list, 115. The current version of the program. So if I go here to bonding characteristics of carbon. So here's, these are now, on the right side, you see the student worksheet. You see here questions, they're fields. I will, here the student, if you do this in a student lab, I'm now here typing in answers randomly. Then I can go to the bottom, I can do either print answers, student fills in the name, student ID, it can be printed, or save answers, HTML. And you could email it to the instructor. It's not wired for all like some sort of text drilling websites now for textbooks where it's all automated. It's not like that. It's a more manual thing. But to get 1,000 emails from 1,000 students, it's probably would be hard to process. So we simply can accommodate that. But and so the goal here is to actually convey a little bit, what is by comparing carbon-carbon bonds, silicon-silicon bonds. Why is it, that there's this enormous variety of carbon-carbon compounds. I think we know at 100 million compounds. Recently, we passed that in the chemical abstracts. So in the instructor's version of the program, I click on answers, and the answers will pop up here on the right side. The student version, the answers are not available. So, and so that's I go back here. So that was my that sort of was a quick glimpse of the various dimensions of the program. So 2 computational engines, about 1,000 compounds pre-built, 3,000 models total, and the ability to do your own thing. So just like basically we are trying to get it all possible ways. We just like even in a program like Spartan or Gaussian, you can do your own thing. At the same time, we provide, the attraction-free water molecules. We provide, canned content. You can sort of use out of the box. It's not at a. That's an important point. It's not at a very specific level, grade level, or it's a pick and choose type thing. So you decide what works for you. We are not trying to. To have something that's, for a very specific target audience. The program is used by all kinds of people, and it's simply logistically impossible for us, to have different versions for every possible, type of audience. I mean, we are a small company, and it's not, that's not doable. So it's you. So we give you, a large library of stuff, and you grab from that, what will work for you. So there, if you, especially with a computational chemistry background, you'll find lots of stuff in there you'll love. But it's pick and choose type thing. There are four buttons here I just mentioned for completeness. So I mean, for Japanese customers, we have some Japanese content, we have some Spanish language content, we have some German language content. The last button here is the program is integrated with Canadian introductory chemistry textbook, Mahaffey et al. Chemistry of Human Activity, Chemical Reactivity. It's a book which integrates general and organic from the very beginning. So organic chemistry is not in this sort of I don't know what you do at your college, whether you do it so it's a traditional way, or I mean many places now they almost try to reverse it now. Do organic before you do the general one, or they at least try to integrate it. So this Canadian book does that too. They see two editions for the. So these are activities you see here, which so you'll see sometimes content which is specific to this textbook. So which is sort of interesting also to read around, and for which you don't see elsewhere in the program. So.